In this session, as a continuation of classification of engineering materials, here we are going to learn about the classification of alloy steels. Steel are alloy of iron and carbon. Apart from that, silicon, manganese, sulfur and nickel are some of the other elements available in steel. Three organizations have specified steel. One is American Iron and Steel Institute, Society of Automotive Engineering, and another one is American Society for Testing and Material. Alloy steels. Alloy steels mean any steel other than carbon steels, that is plain carbon steel. Other than that, other steels are called as alloy steels. The steel products manual defines alloy steels as steels that exceed one or more of the following limits, that is manganese 1.65%, silicon 0.60%, copper 0.60%. Also, a steel is considered to be an alloy steel if a definite amount or minimum of other alloying element is specified or required. Some of the alloying elements are chromium, nickel, molybdenum, vanadium, tungsten, cobalt, boron, copper and others. Low alloy steels. In this steel, 3 to 4% of any one of the alloying elements or more alloying elements are available. The presence of alloying elements provide enhanced properties such as increased strength without loss of toughness and increased hardenability. Types of low alloy steels are AISI steels, HSLA steels. So we look into further. Low alloy steels contain up to 3 to 4% of one or more alloying element, and this having similar microstructure and requires similar heat treatment that of plain carbon steels. They are also referred as piezoelectric alloy steels, and the presence of alloying element obviously will increase the enhanced that is the property and their strength like toughness and increased hardenability, so on. And we'll come to ASI steels, that is one of the classification of low alloy steel is American Iron and Steel Institute steel, which is named after it, and these steels are steel that are generally used in machine construction. ASI steels are sometimes also referred as construction steels or structural steels, and ASI steels have less than about 5% total addition of elements such as the chromium, nickel, copper, molybdenum, vanadium, etc. The property of major interest in this ASI steel group is hardenability. Other classification of low alloy steel is high strength low alloy steel, which is commonly called as HSLA steel or otherwise called as micro-alloyed steels. Some of the major grain refinement are aluminum, vanadium, etc. High alloy steels. High alloy steels are steels which contain more than 5% of one or more alloying element. They have different microstructure and require different heat treatment than that of the plain carbon steels. Types of high alloy steels are tool and die steels, stainless steels. So, high alloy steels are steels which contain more than 5% of one or more alloying element. They have different microstructure and different heat treatment they require than that of plain carbon steel. Their room temperature structures after normalizing may be austenitic, martensitic, or contain precipitated carbides. Next one is tool and die steels. Tool steels are high quality alloys used for tools, dies, etc., which require special character of hardenability, wear resistance, resistance to softening on heating, and like. Stainless steels are used for improving corrosion resistance. Effect of alloying element in steels. Alloying elements are added to steel in small percentages usually less than 5% to improve strength or hardenability. The properties of all steels are determined by the kind and amount of phase of which they are composed by the properties of the phase. The alloying elements in steel affect the stability of these phases, the relative amount of the phases, and how the phases are distributed. What is the purpose of alloying? It is we need to improve or increase hardenability and toughness. We need to improve the resistance to abrasion and wear, to improve machinability and ductility, and so on. Effect of alloying elements are solid solution formation, carbide formation, shifting of critical temperature, effect of hardenability, effect of grain growth, etc. Some of the alloying elements we look into as a glance. First, we focus on manganese. It is a deoxidizer, desulfurizer, and removes the harmful effect of sulfur. Its small amount increases the hardness, strength, and wear resistance. Applications are jaw crushers, stone crushers, rock drills, railway cross points. Next alloying element is silicon. Its typical range in alloy steels are 2%. It acts as an deoxidizer used in steel making. Silicon is less effective than manganese in increasing its rolled strength and hardness. Silicon increases magnetic and electrical property. Silicon increases hardenability, and so on. Next alloying element is chromium. In the range of chromium in alloy steels are 0.3 to 4%. It has its own properties, that is enriched property like deep hardening and good wear resistance. It is very good corrosion resistance, oxidation resistance, and it increases hardenability, improves high temperature strength. Some of the application of this alloy steels are mentioned here, and some of the molybdenum is another alloying element which is reduces temper brittleness. It increases hardenability and machinability of carbon steel. It increases strength and impact resistance. Copper, they are one of the alloying element in alloy steels, which a range of 0.2 to 0.5%. It increases strength, increases the corrosion resistance, and main thing is cast steel to improve. It is added to cast steel to improve fluidity, castability, and strength. Vanadium as an alloying element, it promotes fine grain size. It forms hard carbide. It toughens and strengthens the steel. Nickel as another alloying element which has a strengthen unquenches or annealed steel, toughness and hardenability increased, improves resistance to fatigue failure. Some of the application of those alloy steels are crankshaft, axles, connecting rods, and gears. Some of the property of tungsten as increased hardness, promotes fine grain, resists heat, promotes strength at elevated temperatures, and so on. Titanium as an alloying element, and it has its own impact. And phosphorus, sulfur are similarly as used as an alloying element. Lead, boron, aluminum are the alloying elements. Now we move on to the next major category of ferrous metal, which is stainless steel. Stainless steels are alloys of iron, chromium, and other elements that resist corrosion from many environments. Stainless steels are also known as corrosion resistant steels or chromium bearing steels. What is the effect of chromium on stainless steel? All true stainless steel contain minimum of about 11.5% chromium. This 11.5% chromium permits a thin protective surface layer of chromium oxide to form when the steel is exposed to oxygen. So this chromium acts as an which in terms of chromium oxide, which form a layer which will act as a deoxidizer, and that's what mentioned here. And some of the other elements apart from corrosion are copper, aluminum, silicon, etc. And types of stainless steel are of three kinds depending upon the predominant phase constituent of the microstructure are austenitic stainless steel, ferritic stainless steel, and martensitic stainless steels. Further, we look into that. What is austenitic stainless steel? It has austenitic microstructure. When you view in electron microscope, it will have a austenitic structure. Further slides will show you the picture of austenitic, ferritic and martensitic microstructure, how it will be and its shape. And as of now, we'll see the properties and compositions. So composition of austenitic stainless steel are, when you look at the copper, it is when you look at this carbon, it is 0.03 to 0.25%, and manganese it is 2 to 10%, chromium it is 16 to 26%, and other elements are mentioned. Like applications of this austenitic stainless steel are in various aircraft engine parts, chemical processing industries, food processing industries, and all the dairy industries, transportation, household items, etc. And ferritic stainless steel, they possess a microstructure which is primarily a ferritic microstructure. Ferritic stainless steel have a low carbon to chromium ratio. This eliminates the effect of thermal transformation and prevents hardening by heat treatment. And the compositions are mentioned below, like this carbon 0.08 to 0.2%, silicon and manganese and chromium. And the properties are, they are magnetic, they have good ductility. They have great strength, toughness, and good resistance to corrosion. These steels can be welded, forged, rolled, and machined. Some of the few applications are mentioned here in petroleum industries, in furnace applications, and interior decorative works, screws, fittings, and etc. And finally, the third type of stainless steels are martensitic stainless steel, which possesses a martensitic microstructure in the hardened condition. And these steels are magnetic in all conditions, possess a better and thermal conductivity of all the stainless steel types. Hardness, ductility, and ability to hold an edge are characteristics of martensitic steels. Some of the compositions are mentioned here. Right from carbon, it is 0.15% to 1.2%, silicon 1%, manganese 1%, chromium 11.5 to 18%. And the properties of martensitic stainless steels are good hardness, ductility, thermal conductivity, and it has good toughness and corrosion resistance. Some of the applications are mentioned here are pumps and valve parts. It is used in rolls and tapes, turbine buckets, surgical instruments, etc. And the final classification of stainless steel is duplex stainless steel, which is a mixture of the BCC ferrite and FCC austenite crystal structure. It is a combination of BCC ferrite and FCC austenite crystal structure. The percentage of each phase is dependent on the composition heat treatment. Mostly it is of 40 to 60 ratio, that is percentage here. Most duplex stainless steel are intended to contain around equal amount of ferrite and austenite phase in the annealed condition. Primary alloying elements are chromium and nickel. Duplex stainless steel generally have similar corrosion resistance to austenitic alloys. So this is a picture, and I like to show you that is it shows the microstructure of under micrometer of ferritic, austenitic, martensitic, and duplex classification of stainless steels.